I thought for a long time I could have the record for the loudest snap.
Dang.
But I don't think it's quite loud enough. I hope this is on the recorded.
It all is getting recorded, absolutely. Yeah, we got a great intro today for our recording. We're competing for world records. All righty. All right, so we've had a request here for looking at the band theory, right, assignment. So shoot away. Which ones did you want to look over? You had mentioned the decane one. We'll get to that in a second because that's kind of towards the end. You had mentioned something about SP bands. You want to do one with beryllium or lithium? Chromium, SD band, and then maybe melting points, something like that. All right, so we can get an idea of this band theory. Okay, cool. If you look here, how do we do on bond order? Because that's related to SP band, looking at melting point. Do we remember what bond order is? You can Google it real quick, right? I mean, that's a pretty acceptable way, right, to relearn the information that you've learned previously. You did bond order probably in organic chemistry when you're trying to figure out whether it was a single bond, a double bond, or a triple bond. Okay, and so we will go through and look at that real quick. So bond order. Or maybe some just say BO. Not to be confused with body odor, but bond order. Okay, this is what? Number of what? Minus number of what divided by 2. Exactly right. Yeah, number of bonding orbitals, right? So we'll just call that bonding orbitals. And that's a minus sign number of anti-bonding orbitals. And if you think about that, the idea there, right, is to say that when you have a higher bonding order, you're going to have a stronger bond. So if I get a bonding order of 1, single bond, bonding order of 2, double bond, bonding order of 3, triple bond, bonding order of 1.5, probably some type of resonance structure. If you remember back to the organic chemistry, right? Some type of resonance structure, meaning like, yeah, that double bond could kind of move around, right, to different parts on your particular molecule. All right, so that's going to be related to getting to melting point. If you look at, let's say here, we want to do one for beryllium, right? Okay, so your bands, just see here. If the occupancy is less than 10%, there aren't enough electrons to conduct much. If it's more than 90%, they start interfering with each other's movement. So let me manage the part here. So let me share with you at home what we're looking at. Let's do the screen. Okay, so we're looking at that question right there, or that statement right there that I just read out aloud like that. All right, so does your band structure occupy predict that lithium is a particular metal? So what did we have up here for lithium? And I'm going to have to pull this up online, it looks like. Let me do that real quick. Yeah, move. Perfect. Going back to week 12, just a second. Okay. This is one of the pictures that didn't show up on the PDF. All right, there we go. All right, cool. So this is your valence orbitals in lithium. Okay. And so what are you looking at right there? Are you looking at S bands? Are you looking at P bands? What are you looking at right there for those valence shells for lithium? Okay. So if you're looking at basically why we say about 50%, right? So if you went back up to this graph right here, right? Whenever you're filling in either one lithium atom or lithium, really lithium 2, lithium 4, lithium 8, your bottom half are all filled, right? So all of your bonding orbitals, everything below that dashed line, right, would be a bonding orbital. So you have basically half of your shells filled, right? So we could maybe think about this being something like, okay, so if you had a S band, this would be lithium, and you'd be looking at, say, your S band. And that would be the valence band. You're not looking at the core electrons, your first two, you're looking at the valence, right? So we'd have something like this, right? And this would be indicate that this is more like my, uh, if you want to think about it, more of like, say, your bonding and anti-bonding. In a way. And we call them bands, right? Because you get up to like, a mole of atoms, right? Your difference in energy gap between the bonding and the anti-bonding pretty much virtually disappears, right? There's always some electrons that are able to occupy both, right? Your conduction band, which is located down there, right, below, and your valence band above, all right? Let me make sure, so we'll go back to here. Oh, where'd you go? There we go. Okay, so right, there you go. So your valence band below and your conduction band above, right? And we're kind of in this metal region right here where you don't have really, you have that overlap between your valence band and conduction band. All right. So if we think about that then for beryllium, okay, you look at a periodic table. Periodic table. All right, so beryllium just has one more electron, right? Okay, so when it has one more electron, right, in your S shell, what kind of shading does that look like? Almost completely shaded, right? All of your electrons, in other words, your electrons would be filling up your lower band, right, and your upper conduction band. So I'm not going to redraw that. Okay, completely shaded in, right? Does it predict that you would have some type of metallic conduction if you just based it off of that S band? We bet 100%, right? And if you're at 100%, then you're going to have interference, right? You almost have too many electrons, too many sea of electrons that are packed in there that can't allow them to freely move, right? So now we're going to look at the SP band, right? In other words, we're going to look at the fact that now instead of your electrons just being able to fill S shells, right? You could fit SP shells. So shading the S band, okay, we've already done that. It has empty P valence shells. So let's think about for an SP band, how many electrons could you fit? Let's say for the S electrons, right, that you're fitting, if you had two berylliums, right, you would have a total of 4 electrons, okay? If you had, and if you had that in just your bonding and anti-bonding levels. Okay, so bonding you'd have 2, anti-bonding you would have 2 if you had a beryllium and you're just looking at the S, right? So you would have a total of 4. Okay, now if we go to include the p band, right? How many electrons can you fit in the p orbitals? 6, right? Okay, so now you're up to a total of, if you have 2 of them, right, you're up to a total of 16, right? Or 8 for each atom of beryllium, okay? All right, so if we looked at this then for the SP band, let's go over to the notes and draw this one in. So now we're looking at, say, beryllium, and we're going to look at the SP band. Again, the S band would be just 100% shaded in. So we're not going to draw that up here. But if you did the SP band, you looked at a similar type of rectangle. Like that, okay? How many electrons? So over here in our lithium S band, if you had say like lithium 2, we're thinking about basically having, 2 electrons down here and 2 empty shells above, right? So if we're thinking about this whole thing holding, right, maybe about 16 electrons, okay, in your sp band for 2 beryllium atoms, how many do you have? 4, right? Exactly right. You got 4 in your valence shell, right? And that means that I would have this about 25% full. So I might draw this in something like this, right? Okay. Now, does that qualify as a metal? It's above 10%, right? It's below 90%. Boom, right? We have some ability. So this is just beryllium 2. If you went to, again, a mole of beryllium atoms, you would have an enormous number of electrons. You would have this nice, no really energy gap between your valence and your conduction band, right? So you'd have this good overlap. Okay, what else? So if you went to lithium, what percentage of lithium would be filled up in that box? Yeah, 12.5%, right? Instead of about 25%. Okay. So we still have a little bit above 10%, right? But that does maybe show you why beryllium is a better conductor than lithium, right? Because now we have a few more electrons that are occupying that sp band, right? So they're able to conduct a little bit better. Okay. You also have a little bit, think about bonding order. Yeah, okay. If you're thinking about sp bonding order, you have a little bit better bonding order for beryllium. Okay, all right, so. Oh, okay, so let's do lithium. Actually, I take that back completely. If you're thinking about bond order for lithium versus beryllium, how did you do that part? And if I guess if you just looked at, so we're looking at when we did the homonuclear diatomics, diatomics meaning 2, right? We were able to calculate the bound order from the molecular orbital diagram. Which type of orbitals, bonding antibonding electrons occupying in lithium? All right, so let's answer that question first. Which type of orbitals, bonding or antibonding, are electrons occupying in lithium? All bonding, right? Okay, so we would have a higher bonding order compared to beryllium. What do we have for beryllium? I guess we can answer the second question there. What percent occupancy is the cutoff between bonding and anti-bonding? 50%. Okay, 50% are bonding, 50% are anti-bonding. And then you have, based on your percent occupancy, which metal should have the higher bond order, lithium or beryllium? Does beryllium have, if you're just looking at, again, that 1s level, okay, where we had beryllium at 100%, you had lithium at 50%, okay, which one's going to have a higher bond order? Lithium, right? Because it doesn't have any electrons in that anti-bonding orbital, right? Okay, so you're going to have less there, all right? Cool. By the way, it's the same for the, think about that. If you go to SP, yeah, we're going to leave it as S. All right, never mind. Moving on. Similarly, all transition metals are viewed as having SD bands. What is the maximum number of electrons in an SD band? It does not. Exactly right. Yeah, so 12 electrons in your SD band, 2 for S, 10 for D, right? So you got a total of 12 there. So if you're looking at chromium, right, and I go back to my periodic table, I got 1, 2, 3, 4, 5, 6. I have 6 out of 12, right? So I'm exactly 50%. That's a very, very strong, right, type of bond order. All my electrons are in the number of bonding orbitals, right, is higher. Okay. So if you looked at then, anyway, so chromium would be about 50%. So if we go here and do we see which one has the highest melting point? Chromium does, right? Okay. So what could we look at this and how can we fill this up? All right, well, this is looking at our SD bands. So a total of 12 electrons. If you looked at potassium that we started with, that would have 1, right? So 1 out of 12, you're roughly shaded in 1 out of 12. Calcium, 2 out of 12. scanning them. We're just going up, right? 3 out of 12, 4 out of 12, 5 out of 12, 6 out of 12. The idea, though, is as you fill up bonding orbitals, what happens to your melting point? It's increasing, right? Because you're increasing your bond order, okay? You are having more of your electrons, right, located in those lower energy bonding orbitals, which is allowing, right, for a lowering, right, of your, or a stronger bond to be formed. We'll keep it at that, okay? And then what happens when you get to manganese? Mn. How many electrons there? 7, right? What's that one extra electron going into? In other words, you guys said chromium is 50%, right? So all the electrons in chromium fill up all of your bonding orbitals, right? What happens when you get to manganese? It goes into an antibonding. What happens to your bond order? It goes down a little bit, right? And so now does that do? That weakens, right, your particular strength of your bond. And what do we mean by bonds? I'm kind of avoiding it a little bit. You're meaning that the strength of the lattice. That is all the positive ions, okay? So when we have about half of your SD band filled, that means we have enough electrons to kind of fit between the positive charges, right? That minimizes that repulsion, okay? And keeps them locked in together, okay? While some of the other electrons, right, are free to jump up to that conduction band and freely move, right? All right, so manganese, then you go to iron. Hey, now you have 2 electrons in an antibonding orbital. Cobalt, you have 3 in an antibonding orbital, all the way to zinc, where you have 6 electrons in a antibonding orbital, okay? So we have less stability, right? And when we get to zinc. So as you can see here, basically you should have a shaded in region where you get to 50% at chromium and you go all the way up to 100%, right? All the way shaded in when you get over to zinc. I think the question about mercury as a liquid is an interesting one. Why might mercury be a liquid? Take that same idea that we just did there, right, for the 4th row on the periodic table, or the 3D level, right, where you're looking at, we were looking at potassium through zinc, go down 4, or go down 2 rows, right, and now you're looking where mercury is over there at 80. How could you put that into words? Why might mercury be a liquid at room temperature? Yep, yep, correct. And therefore you have a much lower melting point. You have a melting point that is below room temperature. And as you go down, also, right, as you go down in the periodic table, what are you doing? You're going farther away, right, from the central part of your nucleus, right? And what's that going to result in? That's going to result in antibonding orbitals that are actually higher, right, in energy. So as you fill those up, right, that's drastically decreasing the strength of your bond. All right. Okay, and then you had a question about decane, right? Okay, so if you look at decane right here, let's go over here to our notes to do this one. I'm not going to redraw it because that would be crazy number of lines. But if we just look at C10, H22, okay? How many valence electrons? I would agree with that. Okay, 62 valence electrons. 4 for each carbon. That gets you to 40 plus 22. That gets you to 62. Okay, so 62 valence electrons. And if you go back to, where we go here, okay, You're doing the ridiculous task of kind of filling in 62 electrons. Okay. How many orbitals do you have here? We got 1, 2, 3, 4, 22 on the 22 on this very bottom, and then on the middle next row. So you'd be at 32, 10 and 32. All right. That's what, 64? 64 spots for electrons to occupy. You said down here 22, and then the next row up 10. So that'd be 32. 32 times 2 would be 64, right? So that means you would have basically all of your bottom row filled. You're going to fill up electrons from the bottom row up. Okay. So you would have every orbital on there, every line on there would have 2 electrons, one up, one down. Okay. And then as we go to the second row, okay, we would have almost all of them filled, right, with the exception of 2 of them. In other words, we would have 2 of them that would have 1 electron each. I think I did that right. Let's see if they're, because we had 30, you said there were 32 of them. I'm not going to count them. So we had 32, 64. Take one off, 31. Yeah, that should work. Really? Trying to think how you get to 100. The question on the floor is how many valence electrons does decane have? Yeah, 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 yeah. I'm thinking through that. I want to make sure I'm right on that. So if we did, okay, you're good. Okay. Did it say 66 or so at 62? 62. All right, great, good, good. All right, so if you said there were, again, 22 on the bottom and then 10, that would be a total of 32, right? So if we took, did 30, in other words, if you did 30, say, orbitals, times 2 electrons per orbital, that would get you 60 electrons, right? You'd have 2 extra, and you'd have 2 other orbitals that are remaining, right? So you would have basically all of them filled, and then you'd have these lone 2 over here that have 1 up and 1 up. Okay? So the idea, if you see it, and I know it is tiny on there, what do you have there? You have a sigma, right? CH bond, okay? And then you have more sigma CH bonds, okay? And then you have a, uh, which in my opinion, I think should be CC, right? Because those would be, I think 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah. So that's a typo on their part, right? This one, this bonding down here should be CC. Because if you think about how many single bonds are there going to be between carbon and something that has 10 carbons, right? You're going to look at single bonds there, right? And so you should you not have 9 right there? 9 single bonds, right? For carbon. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. In my opinion, it probably should only be 9 there, right? Because you think about it, if I have 10 carbons, how many single bonds am I going to have? Carbon bonds am I going to have? I'm going to have 9, right? I'm going to have 1 less than the number of carbons that I have. Okay. So I would expect there to be 9 there. So if that's the case, right, then you would have all of them filled, right? And you wouldn't have any lone pairs. Okay. So there should be, and how many, if you thought about how many carbon hydrogen bonds there should be down here. Exactly right. Yeah. Yeah. There should be 22, right? There should be 10 for basically, there 20, right, for each carbon, and then two at the ends, two extras at the end, right? So if you had here, what I would think there should be here is you should have 22 on the bottom, which would be sigma carbon-hydrogen bonds, right? And then you would have 9 sigma carbon-carbon bonds, okay? They have 10, right? I think there probably should be one less than that. But I'd probably have to go back and look at that to make sure that's right, okay? And then your antibonding carbon-carbon and antibonding carbon-hydrogen would be completely empty, okay? But what do you notice about there? There's a bigger gap, right? Between your bottom row and your top row. So what are you thinking about this as a conductor versus a semiconductor versus an insulator? Yeah, probably be a pretty darn good insulator, right? Hey, because it's going to have that band gap between your valence band and your conduction band. And that makes sense, right? Because what are those where are those electrons at? They're localized, right? In other words, like those electrons are bound in that bond between carbon and carbon and hydrogen. They're not free to move around the whole rest of the metal because there's not that many atoms, right? There's only 10 there in that whole molecule. There's what? 32 atoms, 10 carbons, 22 hydrogens, right? But when you're thinking about a metal, what are you thinking about? You're thinking about a mole of atoms, right? You're thinking about a huge, huge number of atoms. And if when you get to that case, what happens? Right? Your band gap becomes a lot smaller. Any other questions on bond? No? Okay. Correct. Yep. Yeah, once you start filling up that top band, you start decreasing the bond strength. All right. Any other questions on superconductors? Kind of vaguely makes sense. These kind of Cooper pairs. I don't know. You guys give me some feedback. How did you like watching Veritasium for a while? Superconductor videos. Because it's kind of a nice break from math. Okay. Well, I think superconductors obviously are they're a good area of research. Lots of people researching right now. Type 2 superconductors, right? Trying to make something that could be superconducting, that could be at a higher temperature, that could have some of the properties that we need it to have, right? So what are the disadvantages of type 2 superconductors right now? Hmm. Yeah. Yeah, exactly right. So not perfect diamagnetic. In other words, there's certain regions, right, where their magnetic field is allowed to penetrate through them. That's one issue. What's another one? It's related to their like physical properties. Yeah, it's a ceramic type of material, right? You know how brittle ceramic is, right? So you can't really make power lines out of a ceramic material, right? Like how do you repair that? How do you don't want something that's going to break in the middle of a thunderstorm, right? Okay, so the idea is how do we make a room temperature? That would be like the holy grail. You can make like a room temperature, right? Type 2 semiconductor, right? So that way you could conduct electricity with zero, pretty much 0% power loss. I mean, there's nothing. I mean, I don't. You never say never, right? Never say never. The small amount of articles that I've read on superconductors would say that it's highly, highly unlikely, right? Because why, right? Well, what happens when you get to room temperature? You have enough heat, right? You have enough vibration in order for your electrons to hit those interior ions, right? That's what it causes your resistivity to go up when you increase in temperature. That's all it is. Your ions are just moving around more. And when they move around more in an unorganized way, electrons that are trying to make their way through the metal crash into them more often, right? So maybe you get closer to room temperature, right? Like you can get to liquid nitrogen temperatures, or maybe even warmer than that, right? But probably not room temp. But who knows? I mean, they invented that would be a big step forward. Okay, so I just have a little bit of other things for you real quick. In the algebra-based physics course, especially for magnetism, equations are just kind of provided, right, for how magnetic fields get generated. We don't go over the theory of how it is. We just say, hey, there's a moving electric charge. So a moving current, moving charge generates a magnetic field. So the Biot, let me get this right. Yeah, the Biot-Savart law is a empirical law, which should be kind of interesting to you, right, as honors physics students, because it looks a lot like a theoretical law. A lot of time empirical laws have random constants in them, right? There doesn't seem to be any rhyme or reason for how they come up with that equation other than that it fits observations, right? But this is a empirical law. So two scientists basically said, hey, we're going to study how the heck current goes through a wire and where the magnetic fields are generated. So their experiment was literally like, take a wire that I can put electricity through or a current through, and then I'm going to take these incredibly small magnetic measurements, right, for another magnet close to it, and see how much it moves, right? And so they did these, like I said, incredibly detailed, tiny types of experiments where you're measuring very, very small movements in a magnet and how it relates to a magnetic field to come up with that equation that you see on the screen right there, which is change, right? Small change, dB, small change in magnetic field is equal to again, a constant permeability of free space divided by 4 pi times however much current. So you can see they're already there. It's always direct. It's always proportional to current. If I have more current, I have more magnetic field. Hey, and then you have dl. Hey, dl is just basically like the length of your wire. In this case, because you look at the d, you're looking at this very small, right, length, times r. R is a vector, so that what looks like a multiplication sign again is a cross product, right? That's why we're using the right-hand rules, right, to tell us what direction things are. Right? Your cross product, all your cross product is, right, is looking at the multiplication of two things that are perpendicular to one another. Think about your right-hand rules that we've been doing, right? That you have a charge that's moving in a certain direction, magnetic field that is perpendicular to that, and you're multiplying those two together, right, to figure out where your force is, right? All right, so this is the exact same thing. It is a cross product. You're multiplying two things that are perpendicular to each other, okay? And that's what R represents. R represents just some distance that is perpendicular to the direction of that current. Okay, so I have my current going along this wire here. If I have my angle here, theta, right? But if I am perfectly perpendicular, the angle theta would be 90, right? Okay, and so we have it coming out to a certain point. That's that X right there, and that's where we would say our change in magnetic field is. What do you have on the bottom? You have a R squared value, okay? Which is just telling you, right? It's a inverse squared relationship, right? Which means that as we double our distance, what happens to our magnetic field? It goes down by a factor of 4, right? And it's inverse, right? Because we make distance greater and greater and greater. What happens to our magnetic field? It gets smaller and smaller. So where does that angle come into play? That's the cross product, right? In this case, we're looking at a cross product of basically the product of current and length times a vector, right? Times a distance away from that wire. So it comes down here, right? Basically, you're looking at that cross product. That's where that sign of that theta comes in. Because anytime you do the magnitude of a cross product, it's just the two things multiplied together times sine of theta. Okay? The sine of theta is just telling you what part of it is perpendicular. If you have a maximum, then your angle is 90, right? For that change in magnetic field. If you want to decrease, right? The change in magnetic field, make your angle less than 90. Okay. All right. So this is the differential form, right? This is where you're looking at basically small changes, dB, dl. And if you went to and wanted to figure out what was your magnetic field from all the little tiny sections of wire that you would add together, okay? Again, think about calculus, right? What is your dl? Your dl is saying really small sections, right? Really small sections of wire. And if I add all of those really small sections of wire together at that point P away from the wire, that's what I get, right? I'm just integrating, okay, that right there. And my guess is you probably never integrated a vector. I don't remember how to do it. I could look it up in a calculus book, I'm sure, right? Figure it out, okay? So a lot of times, right, we make a simplification, if you will, right? If we can, to try to avoid, right, having to do a vector integral, okay? All right. So on that, I'm going to let you guys, as you being honor students, okay, you can easily work through example 12.1, okay, and you can even work through example 12.2, and then there are some on the assignment that I put. I think it's 16 and 17, okay, deal with that Biot-Sievert law, okay, or Biot-Sievert law, okay. So after you work through those two examples, I think you'll be in good shape, okay, to do 16 and 17. Short current segments, arc of a wire, excellent. Okay. Just as a reminder, okay, when we did a thin straight wire, right, in our regular class, we came up with this equation for a thin straight wire, where your magnetic field was permeability times current divided by 2 pi r. And it kind of looked like that figure right there, right? You're looking at these circles of magnetic field, and they're going to be stronger the closer you are to the wire. They're going to be a little bit weaker, right? The farther you get away from that particular wire. But you can find your magnetic field, and that comes from, again, that Biot-Savart law. Okay, so if you will, let's write that down real quick so we can remember it. Savart law. Okay. And not to get too much into the weeds of the calculus again, but this is Ampere's law. I was going to spend a little bit more time on it, but I love the stuff that we did for the bond order activity. So we'll go over this just a little bit quicker. All right. Okay. What you do in Ampere's law is called a line integral. Okay. So the Biot-Savart law was a vector integral. Okay. Again, beyond the scope of this class that we're doing. This is called a line integral. Okay. So what the heck do we mean by a line integral? This figure actually took me a little bit of time to look at, so let's break it down. You have a wire. This is your thin wire in the center, all right? and coming towards you, going away from you. It's coming towards us, right? Because it has the dot right there. So think of the wire. We're looking down the end of the wire. It's a really long wire. Okay, it's really thin. We're looking down the end of it, and that means that it's creating a magnetic field that is going in a counterclockwise direction. Okay, what do you mean? Say, thumb sticking out, right? Curl my fingers, right? It's going around in that counterclockwise direction. Okay. The figure on the left, A, has a random, if you will, right? Circle, not really a circle, but a random surface, right? That's going around it. And you notice that the loop of wire, or that, I shouldn't say loop, sorry. The straight wire, I, is going through that surface. So imagine the surface is in the plane of the board and it's coming through that particular surface, all right? So what is a line integral? So notice how you have a really small angle. Okay? You have a distance from the wire to the end of the surface, and then you have a dl. This dl is just a small length of that line that makes up the surface around that wire. Okay? So if you were to integrate all of that, right, what would you integrate? You would notice, okay, that everywhere around that orange type of loop there, you would get all in the same direction, right? It would always be in a, if you will, kind of in a counterclockwise direction. Okay. Let's compare that then to what we see in B. Is the current the same? Yeah, loop of wire, the current's the same, right? Our magnetic field shown there in the blue arrow, the same, okay? What's the difference though in this ampere path in? Say bottom right, you can kind of see in as in Nancy right there, okay? It does not contain, right, the loop, the straight wire, right? See how this straight wire right here is not going through that particular loop? And what does that mean? If you were, again, to do this kind of weird triangle type of thing where you're looking at a small angle less than 0, right? Or a small angle greater than 0, okay? Here, what do you notice? You notice that in some cases, because you have an angle that is less than 0, you would be getting a line segment that's pointing in, say, the negative direction. And then you would have over here on the bottom right, you would have a theta angle that's greater than 0. So you would have it going to the right or in the positive direction. In other words, they're pointed in opposite directions, okay? Whereas, if you go back again to A and you look at M, no matter where you put d theta, it's going to be a positive value, okay? And I'm going to have a positive dl, okay, if you will, all right? So you could reason yourself through, what would be the result of B? I have some areas that are positive, I have some areas that are negative. All in all, when you go around that particular line integral, okay, you are going to get a value of 0, okay, for that particular integral, okay? Again, you'd have to probably stare at it a little bit to make a little more sense of it. Okay. Okay. So if we want to do that line integral BDL over those M and N surfaces, what is basically we're replacing the little dl, okay, with B times R times D theta. Where does that come from? Just think about how we defined a radian for an angle. You guys remember that? Remember? Yeah, so if you did like a circle right there, right, and you did something like this, and you did angle theta R, and you did S, right, your theta would be S over R, or it'd be R times theta is equal to S. And see on that figure, the dr times theta is equal to d. Okay, that's what that is. BR d theta. Okay. All right. I think I said that right. Oops, and I messed up the step just a little bit. We don't need that D. Okay. Go. Okay, so for N, you have 0. Okay. For path M, okay, circular, it's around the wire, that value there, just like we did for circular motion, right? If you integrate d theta, what do you get all around like a unit circle? What does it equal in radians? 2 pi, right? That radian angle, when you go all the way around a circle, we say is 2 pi. That's where that 2 pi value is coming from, okay? So when we say that, there you go. If you're wanting to integrate BDL, right? Well, where does that B come from? Does that look familiar to you? That's what we just wrote down, right? Permeability times I divided by 2 pi times R, right? Okay. And then we have a d theta in our, say we're saying our d theta for a surface, okay, where that current is going through, okay, is basically 2 pi, okay? So what cancels out? 2 pi, right? So in other words, the 2 pi here, right, cancels out with the 2 pi in the denominator, and you just get this permeability times I. Why the heck is that useful? Let's look at A real quick. I know I'm slightly out over time, but let's just look at A real quick. Okay? Your magnetic field, okay? In other words, these are lines are showing current going through a particular surface on A. So you see your orange line is kind of going around in a counterclockwise direction. You have 3 amps going up. You have 5 amps going down, okay? You have 2 amps here, right, coming around and going back up, okay? And then you have 4 amps, right, coming through, right, your particular loop. So if we look at A, okay, and we wanted to figure out, right, what our blanking on the word real quick. Let me describe it like this. It doesn't matter that we have multiple different currents in different locations, okay? We could still model this, right, as the certain, we could basically just add them all together to find out our total I that's going through that surface, okay? But some of it is going up, some of it is going down, so we do have to assign a particular direction to it, okay? And we think about our B field going around in that, say, counterclockwise direction, okay? So that means we would say, well, 5 amps is probably in the negative direction, 3 amps is in the positive direction, okay? 4 amps would be in the positive direction, 2 amps would be in the negative direction, okay? We get a net value of 0. Does that make sense? We got 5 up, we got 5 down, we got 2 down. That's a total of 7. We got 3 up and 4 up, total of 7. So a total amount of 0. Okay. So even though these are 4 different wires that are going through this particular surface, if you looked at that as a whole, right, you would say that there's really, right, 0, right, in terms of your line integral of the magnetic field. Okay. That wasn't a fantastic explanation, but I'm already 5 minutes over, so I'm going to go ahead and stop there. All right. Give it a shot. Okay. You're going to have a couple questions on Ampere's law. You have a couple questions on magnetic field for lines. You have a couple questions on the Biot-Savart law. Okay. I think you'll be in good shape, but come find me if you're not. Cool.